For those of you that don't know me, my name is Courtney Holle. I work in the Bridge Division. I've been in Bridge Division, going on 19 years now, in the design section. I am the point of contact for structural items for the traffic structures. Let's see. So welcome. I'm just glad to see everyone here. I'm still taken aback by how many people are here. So with that, I will go ahead and start the updates. Okay. All right, so virtual attendees, you are muted. If you do have questions, submit them through the Q&A, and we will have people on this side speak up to those questions. In-person attendees, make sure that you've registered. It just kind of helps keeping track of everything, as well as the registration list is how I follow up after the meeting and send out the information from this meeting and letting you guys know when everything is online, because all of these presentations will be posted online. There is a coffee bar, cafe. It is through the turnstiles. To get over there, you will have to check in with security to get a temporary badge to do so. I'm letting you guys know that now, so that when we take a break and you're like, okay, I really need that caffeine, you will need to get a badge to get to that side. And an escort, yes. Thank you, Raphael. Lunch will be off-site, and we have an hour and 15 minutes for lunch to help with the commuting to get somewhere and coming back. The restrooms are right outside this door. You should see them if you look at the security guard. They're to the right. Building safety. So we are in this yellow square right here. It's Mustang Island. So if in an event that there is an issue, we will be going out through these main doors in case there's a fire. If there's a weather event, we do go downstairs. So for those of you that are new, I do want just kind of give a brief overview. I know some of you guys have been coming year after year, and I do appreciate that. But I also know there are some new people here. So I do want to let people know kind of what is TASIG, where did it come from, why are we doing it? So it is a joint owner industry forum, and it's aimed at guiding, advancing, and improving ancillary structure aspects. So we're talking about design. So we're talking about your design consultants. We're talking about TxDOT internal designs, fabrication. Our fabricators are a big part of this. This is including, we do review the shop drawings, and so we do work closely with our fabricators on this. And construction, is there a better way to do it? Are there issues in construction? We also have academia, right? We've got a lot of research projects going on right now. You'll get some updates on those. And it's just kind of all of us working together to better understand these structures, make them efficient and in design and fabrication and in construction, and having us all work together so we are having that open communication to talk through it. So as far as our goals, again, industry feedback, industry education, advancing the design fabrication, and any procedural or performance issues that people might be seeing, either in the process itself or the structures. So there is a website. All this information is in the website in more detail if you are interested. There's the website. We also have a TASIG email if you want to reach out to the people who lead this effort. Is over multiple divisions. It's not just a Bridge Division thing. It is over multiple divisions. Again, welcoming you, giving you some updates, kind of where we are. We're going to go over research projects, updates. There's a lot of interest in that last year. And so I think kind of seeing an annually progression of like where we are, what we're looking at, helps the industry as a whole. We will talk about resources. There was an email that was sent out yesterday, fairly late. So I'm not sure that you guys had the opportunity of viewing what was in there, but last year we were trying to get feedback, and there was a comment saying, well, if you sent it beforehand, we'd have time to review it and be able to provide feedback during the meeting. So we did send it out. I will print out some copies. So this is going to be after lunch. So I will print out some copies for those of you that weren't able to look at your email. I didn't have time to look at it. And then we're going to have some trivia over shop drawings and ancillary structures in general, and then close out. After each presentation, group, topic, we will have an open discussion to talk about that or any other questions that you guys have. It is from 9 to 3. Lunch is 11:45 to 1 p.m. An hour and 15 minutes is still a little bit tight, so I do recommend kind of, during the break or something, thinking and planning out what you're going to do for lunch. And with that, we'll go ahead and start with the traffic updates.
All right. My name is Rafael Riojas. I'm the traffic engineering section director. And so under my group, we are responsible for things like the TMU TCD and all the traffic standards. And so while I may not be the subject matter expert for all the traffic standards, our section is responsible for uploading them on the page, and we coordinate a lot with the bridge division. We don't have a lot of standard updates since last year regarding, but I will give you a quick update on some that we do have. All right. So our new safety campaign, we used to have the In the Streak, and so now it's Drive Like a Texan. I don't know if we've seen the videos in-house. I don't know if they've been made public, but maybe since they changed the slide, now they are. And it's just about, being kind, courteous, and safe. I kind of think of I saw it in Chicago on the DMS board. It says like using your turn signal is like the first instant messaging, right? And so I kind of believe in that. Like if I turn on my turn signal, everyone just keeps zoom, zoom, zoom. Like, oh, well, can I get in, please? So I don't know, but think about that. When you're out there driving, be kind, safe, and courteous, and drive responsibly. I think a lot of our crashes are from risky behavior. So let's not try to be one of those people. So one of our sections of sheets that were updated were our electrical detail sheets. These sheets were updated in April of this year. And in that memo, it says that the sheets can be used immediately or beginning with the October letting. So maybe y'all haven't seen these in sets of plans. There's more updates than I'm going to cover, but I tried to cover the ones that are somewhat applicable to what y'all may be interested in. So in general, one of the general comments, change the length of conductors outside of the weatherheads to be 18 inches to 36 inches as required by the electrical utility. On ED sheet 1, clarified that rigid metal conduit minimum burial to 18 inches below grade or bottom of the ground box. On sheet 4, modified the ground box detail to specify concrete without a class. So thinking that's just they can use any class of concrete. Is that correct, Craig? Yeah. And then on ED7, they increased the quantity of the rebar for underground service foundations to satisfy the NEC requirements. On ED11, revised some foundation details to remove callouts associated with rigid metal conduit elbows. And then on the last sheet, revised section AA to show the conduit entering the ground box. And again, the call out for concrete specified without a class. There was one other minor update on the HMID sheets. Those sheets came out in 2024, so we gave an update to that last year. So we had to basically we had to put back what was in the HMIDs from 03. So we had revised a weld in detail G. So here's the whole sheet. I'm going to zoom into like what we changed. So on the top shows the detail, and I don't know what these welding symbols mean. But we moved the little arrow from the top to the bottom. Correct. So we moved it back to what we had in 03. And so that's all the updates that I have, and then Greg's gonna come give an update. Oh, all right.
Okay, so now we're going to go into bridges. These slides are going to look extremely familiar. They're the same slides from last year. We have made a lot of progress in development of some of these. What we have on here is like upcoming design specifications. But standards take a lot of effort from a lot of different people. We go through a lot of different reviews because once we post them, we want to make sure that everyone's had time to look at it, comment on them, and there's been discussions. We don't want to put something out there that's going to surprise the industry, let's put it that way. So you will see that some of our standards are still to the luminaire traffic signal signs support specification, otherwise known as LTS. The third edition, which is from 1994, the HMIPs were updated for like fatigue details and stuff like that, but we're formally through the design process, through the checking, we're at the sheets. So we're addressing the red lines and then internal review, and then it'll go out for industry review. And it'll be industry review, 95%, take two. So they were sent out and then we got feedback from the industry, and it took us some time to kind of incorporate that feedback. So we are on our way there. One of the next ones we're going to be putting our effort to is the roadway illumination poles and getting that really to LRFD. So we're looking at the LTS 3 and 6, that's going to be the standard spec using stress design, going to LRFD using the resistance design. And the first one that we really started our feed into on this one is probably one of the largest pockets. And so this was the cost and OSB, so the overhead sign supports. And we worked through over multiple years with our consultants to get designs and to get the philosophy documented. And we have, design examples for it, and we've got those standards. Some of that is what I sent out yesterday. Those are the design tables, and I'll go a little bit more into that. But we do have those sheets. We do have alternates or options for like multi-sided and tapered, because we're doing a lot of alternate calculations and reviewing those during our shop drawing review. And so we have incorporated that kind of into the update when we go to LRFD for this. And so we learned a lot during that process. And so now we feel confident that, moving forward with these other ones, moving into LRFD, we're in a good place to do that. So that's kind of our next step with anything that we start now. We do have wind maps for the LRFD. We're waiting to post them until we we have standards that correlate with them. So when we do the cost and the OSBs. Here are some of the other ones that we're looking into, which is the DMS attachment details, the truss to concrete column connection details. This is another one we've been working on for a while. We came up with sheets. We sent it to the contractors. They had feedback as far as like the number of connections or how it's presented, because we were doing the idea of, well, we have the design, so refer to the standard. And they're like, well, can we simplify it? Can we make it easier and more repetitive for construction? And so we are working on that. And the last time when we were talking about it, we did end up, we're designing two different truss to column connections. One where you have the steel post that you put on top of a concrete column, and one with embedded angles into the concrete, because those are the two main ones that people were using. We wanted to make sure that we could standardize those. So that kind of gives you an idea of where we are, where we're going as far as our standards are concerned. And then with that, I will pass it off to Mark for maintenance slides.
Okay, good morning, everyone. Yeah, Mark Johnson. I'm out of the maintenance division here at this campus. I work with MMS data. If you're not familiar, basically we take in data for all the activities we do in maintenance, both through in-house crews, TxDOT folks with the orange shirts on, and through routine maintenance contracts. We try to consolidate that data. We really put in significant efforts to QC that data every year so we can come back and say exactly how much money is being spent on various different activities, as well as quantities of activities, whether it's how many trees we've cut down or how many potholes we patched or how many bridge joints that we have sealed, all those types of things. We try to really put in a lot of effort to get that data to be correct. So I want to show you a few things from the side of maintenance, since this topic always comes up. Talk a little bit about what our data shows in terms of structures and also in terms of our budget. So these numbers at the bottom, when you see 732, 742, like when I came up through the agency, I was very familiar with the TxDOT spec book. Then I came to maintenance and find out that they have a whole different system of tracking these activities, which was largely confusing. First thought, only the government could make this complicated. But these are actual numbers that we use in maintenance for tracking activities. There's thousands of spec items and bid codes. We have about 100 activities in MMS. And really, of the 100, there's about 30 or 40 of them that are common. So when you see 732, that just represents in maintenance how much money is being spent on maintaining large signs. There's 4 categories. We've got large signs, we've got traffic signals, illumination, and ITS. And you can see over time, I just went back and pulled data over the last 4 years. 2025 fiscal year is obviously not quite complete yet. Our fiscal year ends at the end of August. But you see the general trend lines, which is, to me, is that there's not. It's pretty consistent from year to year as far as how much money we're spending on these activities. No doubt we are spending more money in maintaining traffic signals. That doesn't mean structural work per se. It just means that we're spending more money, and could be signal timing, could be replacing signal heads, wiring, trying to get signals out of flash, all those types of things that happen during storm events. But certainly spending more money on traffic signals than we do in the other categories. Illumination, fairly consistent. I was somewhat surprised by that, roughly about $15 million per year. We have very much been in a period where we are upgrading luminaires to LED technology. That process is ongoing, and we're pretty close to being there, is my understanding, right?
Yeah, all the TxDOT should be LED.
We are there now. Okay, there's the update with the luminaires, huh? So yeah, just kind of wanted to give you an update of what we're looking at in terms of the money. Not as much money spent on ITS and large signs. This is just data coming in from maintenance contracts, to be clear. So if we were doing work on large signs or even luminaires on a construction contract, this data does not reflect that kind of work. Our budget, we are moving in FY26, beginning next month. Every 2 years, we go through a process where we request funding through the legislature as far as how much money we need to maintain our network. We're going to be getting close to $1.8 billion this year. That's the most money we've ever had. When I came to maintenance about 6 years ago, it was less than 1.5 billion. As you can see, we were trending upwards. We certainly went through that period of a lot of inflation a couple of years ago, and we're scrambling through that process, finding that we were spending just as much money and getting a whole lot less done due to the effects of inflation. And our network continues to grow over time as we put in more cable barrier, for example. That costs more money to maintain it. The more cable barrier, the more luminaires that we install. We do have a fairly fairly complex process of how we come up with our budget. We go out, it's all data driven. We go out, we take data on pavement condition scores. We look at that, very closely in terms of how many cracks and ruts there are in the pavement. We look at ride scores, how bumpy is the road. And essentially the way this works is that the worse condition the pavements are in, the greater the request is for money to try to keep our network at a sustainable level. We look at the number of assets we have in terms of traffic signals, luminaires, could be cable barrier and things like that. We look at rainfall, weather patterns and things like that. All of this data is used comprehensively to look and determine how much money that we need. We then come up with a number. We present that to the legislature. Typically, they come back, give us something like 90% of what we ask for. And then we have data structured by each division, and that determines how much money we are going to disseminate out to each of our districts. So it is a fairly complex process, takes several months, but very, very data intensive. I will say also, all of this is being looked at very closely right now as far as how we determine what the budget is. Is the formula correct? This is, as long as I've been at TxDOT, this has been an ongoing debate. You look at one size fits all model. It seems to fit very well in some districts. And then you go back and look at other districts and the money they're getting and find out that our predictions weren't necessarily that accurate when you go back and see where the money got spent. So it's a constant challenge trying to determine how much money do we really need to maintain our network at a serviceable level. And this last bullet here at the bottom, went back and did some bid code analysis. This is probably from a year ago, but when I say there's about $50 million a year being spent in these, what I'll call like structural items, that doesn't mean that we're spending $50 million in fixing foundation cracks and things like that, or base plates on luminaires and high masts. It's something roughly more like $4 million estimated, where we are doing work on large signs. That's really more what I would consider to be structural work. The rest of that money is, again, trying to bring signals back online, trying to upgrade luminaires to LED and those types of activities. The only other thing I really wanted to bring up are the license plate readers. I guess I'll just ask, anybody here not familiar with what these are? Okay, that's fine. I will just start by saying these are, no disclaimer, they are somewhat political. They are becoming more and more popular all over the country. These are being used to fight crime, human trafficking, things like that. Basically, if you're not aware, as you drive around, there are license plate cameras all over the roads. Cities have them everywhere. They're all over the highway now. They are taking a picture of your license plate when you go by. If your vehicle is identified as being involved in some sort of serious crime, it tracks it back to a federal database, and local law enforcement authorities are being alerted immediately that your license plate just went by that reader. Due to the nature of how these are used and the data being taken and the law enforcement purposes involved, there is very much a debate about what is the right way to go about that. I just want to say, like, from TxDOT standpoint, we are neutral in that discussion. We do not have an opinion one way or the other of how the cameras should be used. These are being installed all over our rights of way. You'll see poles on the side of the road. They're not TxDOT poles. They're not TxDOT cameras. The cameras belong to cities. They belong to counties. They belong to DPS, even federal agencies down near the border that they are using for their own law enforcement purposes. We did some data analysis probably a year ago on this. Found out that just last year alone, I think we had permits approved for something like 500 cameras around the state just on TxDOT highways. This was such an issue. This got elevated all the way up to our administration. The program got put on hold for a few months as we were really looking at the data and being collected and making sure that we did not have private parties that were benefiting from the right of way and collecting data. Some of that has been since resolved, and we are back resuming and approving permits. And I can say almost every week we're approving probably anywhere from 20 to 50 cameras all over the state for different cities and counties that are interested in using this technology. I just kind of want to bring this up with this panel here. If you all see these and have any best practices on how to install the infrastructure, some of these don't necessarily have to drill holes into the infrastructure because there's solar panels involved. They try to use the bands around the mast arms or on the luminaire poles. I think that's probably a good thing. Some of these are even on utility poles on the side of the road. Many of them are on their owned infrastructure that basically belongs to the city. They're supposed to maintain those poles. But you will continue to see more and more of these readers around the state, not just on TxDOT highways, but on city streets. Just kind of wanted to highlight that. This is definitely a trend that I came to maintenance in 2019. We were doing these a little bit. I'd see maybe, I don't know, 2 permits a month with a couple of cameras. Now we're seeing 4 or 5 different agreements every week, and each agreement may have 15 or 20 cameras on it. So this technology is really exploding at this point as a means for law enforcement. One other thing with this, because we got so many requests for these, we have stated that we will not be installing these on TxDOT maintained infrastructure. So if you see these on traffic signal poles or even luminaires, not the crash-worthy ones, but the shoe-based type luminaires, they need to be infrastructure that's maintained by the city through a municipal maintenance agreement. If we are maintaining the infrastructure, our division director said we're not putting license plate cameras on it. The cities can put them on a separate pole. But yeah, any questions on any of the budget stuff or the license plate reader cameras? Surprised to see that not all hadn't heard of these, so this is good. Bob, yeah. Yes, so you're talking about the follow-up actions. Right, so we made some changes with that as well through the bridge plan process. Now, we used to have it so there were only certain bridge-centric function codes. Again, these are maintenance activities, and through that process, come to find out, like a lot of them are guardrail repair or even side slope repairs, and now we can charge directly to the bridge. Yeah. Oh, sorry. Okay, so if the work is being done on ancillary structure and it's bridge-related work, I don't have a really good way of knowing that work being done on that luminaire was specifically related to the structure.
More specifically, are y'all tracking overhead sign breaking?
Oh, right. Yeah, so you're talking about like inspection reports and things like that? No. Yeah. Yep. Right. Thanks, y'all.
All right, my name is Greg Jones. I'm with the Traffic Division. In the Traffic Engineering section, I handle lighting and electrical things. And also, I'm the project manager for a consultant contract, statewide contract to inventory and inspect ancillary structures. And it's a 5-year contract. So we started this back in 2020, and at the time, we had no statewide records of large traffic structures. We have all these structures, but we didn't know where they were. We didn't know how many we had, and we didn't know the conditions. So in 2020, we got a contract with Michael Baker International, tasks of inventory inspection and create a database. So they've gone out and inventoried things with structures with LiDAR, and they can get a lot of good information with the LiDAR. Heights and you know, number of sides, all kinds of stuff. And then they're inspecting the ancillary structures, and just due to costs, we've just been inspecting a sampling of structures. We don't have the funds to inspect everything, but we're getting a good idea what's out there, and then put everything in a ArcGIS database. So the ancillary structures, the contract is set up that we can inspect high mast poles, overhead sign structures, ITS poles, signals. For this contract, we focused on high mast poles and overhead sign structures. So it's a 5-year contract, and the end of the contract is just next month. So it's pretty much, we're just at the point of getting our final data into the database. So the high mast poles, in this year, we completed our high mast inventory. We don't have the data for those central West Texas districts yet posted, but we do have the data for that. But overall, we have 6,000 high mast poles, over 6,000 high mast poles, and through our inspection, we inspected about a fourth of those. Overhead sign structures. Let me see. Oops, what happened? Here we go. Yeah, I like that video. So in 2022, that sign on US 75 in North Texas fell over, and it was a base plate weld failure. So MTD division got on that, and they set up a in-house inspection of anchor bolts of cantilever overhead sign structures, and basically it was all TxDOT inspections, and they were just basically supposed to count how many had loose nuts on them. So they also got with us, and we added overhead sign structures to our inventory and inspection, and we focused on Fort Worth and Dallas districts, since that's where we had those failures. And then in 2024, we completed our statewide inventory of overhead sign structures, and we still need to fill in some data, but we have all the data. Houston data will be in there pretty soon. And also in 2025, on MTD's suggestion, we did non-destructive testing in Fort Worth and Dallas of cantilever overhead sign structures to do non-destructive testing of the base plate weld to see if there's any cracks in them. Because the thought was that if there's loose nuts, then maybe that contributed to the failure of the base plate weld. So we did we inspected structures with at least two loose nuts in the Fort Worth and Dallas area. Overall we inspected 87 of those structures with loose nuts, and 15 of them had cracks in the weld to base plate. So that's kind of an example of one that they found. The cracks are usually 1 to 3 inches long, from 1 to 5 cracks in the base plate. So, and we just got that information about a couple of months ago. So we've notified the districts to evaluate, and I'm sure some of those have probably been taken down, but I don't have all the information on that yet. But in the past, when we found structures with major deficiencies, the districts usually just take them down. Okay, the other part of our contract is the GIS database. It's in ArcGIS Online, and it is now on the TxDOT ArcGIS Online system. And we're still getting all the data into it and making sure all the functionality is there. It's mostly working, but anyone in TxDOT can have access to this database. Just get an account through the service desk, and join the group TxDOT, HMI, and OSS inspection reporting. So I think this will be pretty handy for the districts in maintaining their equipment. So this contract is over in September. I'm planning on getting a new one going this next fiscal year to hopefully start in 2027. We'll be adding new construction that's been done since the last round. So we'll do more inspections, and we may add other structure types. Since I'll be getting the scope together, if anyone has any suggestions on what other structure types to be looking at, maybe traffic signals, just get with me on that.
Perfect.
I'll touch anything.
So, okay, yeah, and I appreciate again the opportunity for us to talk. We're 2 years in on a study. We've got 1 year left, and we've been doing a whole bunch of work. And we'll kind of see a little bit of an overview of what we're doing, and hopefully get some good feedback today. As I mentioned, it's a joint study between UT Austin and A&M, and we've got lots and lots of people working on here. When we look at the UT folks that are on here, you can see the students and postdocs that are doing all the heavy lifting and so on. This is UT Austin. My good friend Stefan from A&M likes to call us TU, which it's kind of humbling to have a competing university kind of refer to you as the university and actually have an acronym and so on for that. But anyway, so this is our group that we've got, and we're going to have the speakers going on here, and the folks we have at A&M are listed on this slide here. And it's been a really good project from the perspective. We've had a few different projects where we've had joint studies between UT and A&M, and it's been a really good team. We work together really, really well. And I think you'll kind of see as we go through and the students speak a little bit today that there's been good collaboration between the groups and start the communication and so on that we've had. As you're going to see as we kind of go through the project today, we're providing an overview of really everything that we've been doing up to this stage, and includes we're trying to look at cracks and so on that happen in the welds and so on at the base plates of these different types of structures, and then trying to come up with repair techniques. Now, when you start thinking about what's in the field, we end up having those structural elements seeing continual cycles that are varying in amplitude and things. In the laboratory, we always do things like constant amplitude type tests. And you try to say, well, gee, we did 10,000 cycles or 30,000 cycles, but that doesn't mean much to you physically. So you're going to kind of see as we walk through here, we're going to talk about everything we've been doing, our test results, and try to give you an indication of what this would mean from a performance and so on of the repair techniques that we're doing in the field and so on from a timing and things like that perspective. But again, we're going to have all three students from UT and A&M that are going to be talking a little bit about this, and Jung Hoon's going to start kind of lead us off here then. Okay.
Okay. Hello, my name is Jung Hoon, and let me start with the introduction to this research. So ancillary structures like TSS, coast, and HMIP are exposed to a large number of repetitive load from wind and vehicles throughout their service life. And that repetitive load can cause the fatigue damage to the structures. And if we cannot detect the fatigue damage at an early stage, it can lead to unexpected and severe failures. Yeah. So previous studies reported that the main source of the fatigue damage of TSS and coast is repetitive vibration of the mast arm. And for HMIP, the main source of the fatigue damage has been identified as vortex shedding from wind. To investigate this loading scenario under controlled conditions, many researchers have conducted experimental tests. And typically, this experimental test involves connecting test specimens to a load box and then apply the cyclic loading through an actuator. And these results consistently show that fatigue cracks occur at the weld toe between the base plate and the pole and leads to the brittle fracture. And some researchers have also focused on the galvanizing process, which can introduce a thermal stress. And the research shows that high level of concentration occur at the weld toe during the galvanizing process and can cause the galvanizing crack, which means weld toe is a critical weak area even before the structure is put into service. So despite these clarities, there is a still challenge. Here what we can see is both images have a crack, but on the right side, crack is clearly visible, but on the left side, crack is not visible. The problem is cracks often remain invisible in early stages. So by the time crack is visible, significant damage may have also been occurred. So that's why the early detection is important, but it is difficult. And for that, non-destructive testing, NDT, is essential. In this research, we primarily use the phased array ultrasonic testing, PAUT, as a non-destructive testing. And this technique uses a probe that emit the ultrasonic wave. And when ultrasonic waves encounter a crack, a part of the wave will reflect back. And that signal is captured and visualized. So here is the example of the PAUT result. And from this image, it allows us to identify the cracks locations and the crack size. So after identifying the cracks location, we need to repair it. And previous proposed repair method involved that identifying cracks location and then grinding the existing crack and then restoring the section by rewelding. So the objective of this research can summarize in three main parts. First, conducting field assessment using PAUT in various regions across Texas to confirm that cracks are detectable using PAUT and located at weld toe. And second, conducting lab tests to induce fatigue crack and then repair it, and then evaluate the performance of the repair techniques. And finally, we aim to provide practical recommendations for monitoring, repairing, and potential replacement for these types of structures. So let's move on to the field assessment. We inspected poles in 4 different regions across Texas: Austin, Bryan, Dallas, and Houston. And a total of 120 poles were inspected and 40 for each type of structures. Field assessment involves measuring the structure dimensions first, and then using PAUT to identify the cracks location. So here is the video of the field assessment. First, we apply the couplant gel on the surface, and then attach the probe on the surface and move across the region of interest. And then we can get these kinds of results This is the result of the PAUT. We already measured the thickness of the pole, so we know where the surface line is. So if the signal comes around the surface line, that's how we find where crack is. And these images allow us to measure the crack size. So here is the result of the field assessment from 4 coast specimens. We normalize the layout of the pole, including mast arms orientations and traffic direction. And because of the mast arm sulfate, the opposite side of the mast arm has a tension stress. And the red marks on the diagram indicate the cracks location. So here what we can see is cracks primarily located on the tension side, which means the well-to opposite side of the mast arm is the critical weak area. For TSS, we follow a similar normalization process. And here what we can see is cracks more scattered compared to coast, but still they are concentrated on the tension side, which means that same with coast, well-to on the tension side is a critical weak area. For HMIP, it requires a slightly different approach. Since many HMIP have a ground slip, we visualize them as 2 rings like this. And then we organize the layout based on the predominant wind direction to account for vortex shedding. And cracks located between the base plate and the ground slip were marked on the outside, and those between the pole and ground slip were marked inside. So overall, crack tended to locate it side perpendicular to the predominant wind direction, which supports the idea that vortex shedding is the primary reason of fatigue damage of HMIP. So the findings from field assessment is for TSS and coast, cracks mainly located on the tension side, and for HMIP, cracks mainly occur side perpendicular to predominant wind direction. And now we know where is the critical weak area is, so we can focus our monitoring more effectively. And let's move on to the lab test setup. At UT, the experimental test was planned for HMIP and coast, while Texas A&M is conducting testing for TSS. The test methodology is pretty similar, so I will describe the general test setup. The test specimens were connected both ends of the load box, and then the cyclic loading was applied through an actuator. So on the right, we can see the video of the fatigue test. We can see that actuator just pulling up the loading box. So the top side of the test specimen has a tension stress. So the fatigue cracks will occur over this point. Yep. And throughout the experimental test, we paused at designated intervals to inspect the test specimen using PAUT and measure the length and the depth of the crack. And if the crack exceeds the certain level of threshold, we repair that by grinding and rewelding. Our repair stages fall into 2 main stages. First, pre-rewelding stage and post-rewelding stage. In pre-rewelding stage, one key decision is whether grinding the groove to remove existing crack entirely, or just weld over the crack and allow weld material penetrate into the crack. And post-rewelding stage, we consider a different type of surface treatment. First option was leave weld bit as is, and then second option was grind the weld toe slightly to remove the to reduce the stress concentration and prevent any unexpected undercut. And another option is sand out the surface entirely to remove any irregularities. So we are now comparing this method to determine which method has the best fatigue performance. So with that, I'll hand it over to Xiu Chen, who will present about the results.
Thank you, Jung-Ho. I'm Shou Chen, UT graduate student in this project, and I will share some of current results. Yeah, for HMIP test, we took all 4 of our specimens from in-service HMIPs in Houston. We took them down and cut 14 feet from the base plate upward, and then they were transported to Austin, where the flange plate were welded on, and then mounted them on our test setup. We used 12-sided HMIP specimen. The diameter of base plate is about 49 inches, and the wall thickness is about 0.45 inches. In lab test setup, we applied a stress range of 7 KSI with a controlling amplitude of 0.19 inches at a loading frequency of 1.25 hertz. For comparison, file data of an in-service HMIP in Austin shows its effective stress range of only 0.6 KSI, amplitude of 0.01 inches at the same height, and 26.5 thousand cycles per day. This slide shows how we convert our lab data to file performance by using SN curve. The SN curve on right shows the relationship between the stress range and the number of vertex cycles. And the x-axis of this chart represents the number of vertex cycles, and the y-axis represents the stress range. These different lines represent the different detail categories from Ashto vertex design curve. Here we can see as the stress range decrease, the number of vertex cycle increase. So the equation on the left from the SN curve shows the number of cycles is related to the stress range to the third power. So in our case, our lab test applies stress range of 7 KSI divided by effective stress range in the field of 0.6 KSI qubit, and the result times the number of cycles in the lab equals to number of cycles in the field. And this number of cycles in the field divided by cycles per day equals to duration of HMIP in the field. From the calculations, 10,000 cycles in the lab, 2.5 hours of testing is equivalent to approximately 1.6 years of neutral wind loadings on an in-service HMIP in Austin. I'd like to share some of our results regarding the HMIP test and repair. We focused our test on 2-post 6 bands. However, most of them have undergone only 1 repair. The East HMIP band 2 has undergone 5 repairs. This allows us to share the effectiveness of each repair attempt. The chart on right shows the crack length propagations at East Pole band 2 over the cumulative cycles. The x-axis represents the cumulative cycles, and the y-axis represents the crack length. The blue dashed line is the repair threshold at 2% of circumference. That is 2 inches. For first 2 repaired, wells were made immediately upon the rapid crack growth. After several attempts, we set our repair threshold at 2% of circumference. And this location has been repaired, and the crack reappeared for a total of 5 times. The first repair were performed 50,000 cycles after cracking. The crack depth was measured at 0.1 inches. Here. Our repair involved grinding out the crack and apply 3 well passes, 1 at the bottom and 2 cover passes above it. However, just 20,000 cycles after the first repair, the new crack reappeared between the 2 cover passes. So The second repair was performed 40,000 cycles after the first. This time, the measured crack has reached at 0.05 inches, and the crack located between the two cover passes. And this time, we grind out the weld, grind out the crack along with the previous weld and apply 5 weld passes, 2 fill at the bottom and 3 cover passes above them to distribute the potential stress concentrations. And after this repair, the crack didn't show up for quite well. Eventually, it did. The growth is relatively slow. The third and fourth repair were performed within a short interval. The main goal for third repair is to say if a relatively shallow, like depth of 0.05 or 0.1 inches crack could be repaired by direct welding without grinding. The result wasn't ideal. The crack was merely covered and soon penetrated through the cover passes and reappear on surface. So we decided to conduct the first repair just 30,000 cycles after the third. What we set this repair apart from the earlier ones is that we sanded the weld surface after welding to minimize the stress concentrations. And since the metal in this location has undergone considerable fatigue, the new crack reappeared shortly after. So next, we decided to take the fifth repair. The fifth repair was taken 60,000 cycles after the fourth, and this time the crack was really deep with a depth of 5/16 inches. And we use the same grinding and sanding method as the fourth. And this time we apply a total of 9 weld passes. 1 fill passes at the bottom to fill the crack tip, and two fill passes in the middle, and 2 more layers above them. Each has 3 weld passes. And this repair has been relatively effective so far. Eventually, the new crack appeared. It still remains small and stable. Our test and repair on HMIP are still ongoing and moving forward. We have 2 cold specimens to be tested, which were fabricated by structural and steel products, and they will be connected to a load box at the bottom, and we will examine its crack initiations and repair in this setup as well. And we also conducted some test and repair on TSS. Hangul will be presenting some of these details.
Thank you, Shou-chan. Hi, my name is Hangul Kim, and I want to present about the test results for traffic signal poles, which is done by Texas A&M University. This is our setup. The setup resembles to the HMIP setup, so let me skip the detailed explanation for the setup. We have tested 2 poles. West pole is multi-sided pole with 8 sides, and the east pole is round pole. Their dimensions are shown on the right side. We have a table at the bottom, and it is showing the test setup for each side. We tested side 1 at the first time with stress range of 15 KSI, and we found that crack propagated so fast under this 15 KSI. So we wanted to decrease it to 10 KSI when we started testing other sides. We also set the loading stress and frequency based on the stress range. During the past, we did inspection for every 2,000 of cycles by doing visual inspection and PAUT. We used the acetone for the visual inspection. While the pole is under cyclic loading, we put the acetone, checking if it is seeping into or out of the crack openings. We also use the PAUT, and its sample of the results is shown on the right side. Based on the inspection results, we could plot crack depths and crack lengths against the number of cycles. The left plot is showing the crack depth in terms of the percentage of the wall thickness, and it was measured by PAUT. The right plot is showing the crack length in terms of the inches, and it was measured by the visual inspection using acetone. It also has the blue dashed line. It represents the repair threshold, which is 2% of the circumference for the crack length. When the crack length exceeded this threshold, we wanted to start repairing. Before we start repairing process, we wanted to double check the crack location by doing dye penetration test. It is one of the non-destructive testing methods, so we spray the visible dye, letting it penetrate into the surface defect. And based on the penetrated dye, we can check the crack location as shown on the picture. After this, we ground and grooved the location, then welded it. The repairing followed this procedure, which has been developed by cooperation of 2 institutions. After some tests, we could get this result. The plot is showing life in terms of years on its y-axis. It was converted by the life conversion using the same methods that Xiu-Chan has explained in previous slide. In the x-axis, these are presenting the crack locations as explained on the right side. From M1 to M5 are the crack locations on the multi-sided pole. From R1 to R3 are for the round pole. In the plot, we have 2 types of sections. The hatchet section representing the pre-repair life, which is from the starting of the test until the occurrence of the first critical crack on the connection, on the weld. And this clear section is representing the post-repair life, which is from the moment of the repair until the occurrence of the second critical crack on the connection. It could be a little bit alarming that when we see the pre-repair life, the hatchet section is remaining less than 20 years or even less than 1 year. But when we consider that these poles are from the field and they were in the service previously, that would be not that much surprising. About these clear sections, the post-repair life, you may see the variation in this post-repair life. It is from 1 to 15 years, but it was largely due to the differences in welding parameters in repair process. At the time, we were refining our welding techniques, including welding speed, welding rods, or welding amperes to achieve a consistent result. But even with this variation, it is clear that repair can extend the fatigue life. This is after completing the test for those poles, we also want to do additional tests for the 2 fabricated round poles as shown on the picture. Their dimensions are shown on the slide. This is what we found from the experimental test so far. We found that multi-sided pole has this fatigue crack initiated from the bend, and we also confirmed that repair can extend the fatigue life. From the traffic signal poles test, we found that round pole could have better fatigue performance than the multi-sided pole. So far, I presented about the test results, and let me present about the conclusion and future work from now on. This is the conclusion that we've got for the last 2 years of the project. From the field assessment, we found that traffic signal poles and coast structures commonly have their fatigue cracks on the tension side. For the HMIP, we found that fatigue cracks commonly occurs at the perpendicular to the predominant wind direction. From experimental tests, we found that multi-sided poles has their fatigue cracks initiated from the bend, and we also confirmed that repair can extend the fatigue life of the pole. This is the future work that we want to complete in next 1 year. We want to complete the experimental test, develop the certification method for inspectors, and finalize guidance on crack mitigation, repair, or replacement. To do so, we want to identify what is the effective repairing method or what is the optimal repairing timing. If you have any questions for this project, you can contact these people. This is what we prepared for today. Thank you for your attention.
Morning, everyone. My name is Alex Higginbotham. I'll be representing the TTI team to discuss our progress on the project to develop performance of faceplate connections and costs and traffic signal structures. Our TTI team is headed off by Dr. Stefan Herlevaus, and we're also working with UT El Paso, and Wade Odell's our TxDOT committee project manager. So just to give you an idea where we're going with this presentation, a brief outline. We'll start with some background of the project, where the problem was, different things we considered in trying to fix the problem. Then we'll discuss two design alternates that we're doing research into and we're evaluating. The first being our fail-safe system, the next being our structural fatigue improvement. Then we'll go into some experimental testing that we've been doing, the progress on that. And lastly, we'll discuss a database of cost structures that we've been developing with some of the same parameters and some different parameters that were discussed earlier. So some background, as has been discussed, there's been some cantilever structures that have failed in Texas in the past years, with the cost structure failing in Dallas that was previously mentioned after about 11 years of service, as well as two TSS that failed after only 2 years of service. The reasons that we're investigating for this is, again, potential fatigue in the pole to base plate connection. Both these types of structures use socket connections as pictured in the bottom right due to their economy, but these types of connections tend to not have as good of a fatigue life, and their fatigue life isn't as well understood. And so a lot of the hope for this project is to really better understand the fatigue life as well as seek how we can improve it. So there was an industry advisor group meeting in the spring of 2024 to really discuss what good methods would be to try to tackle this problem. There were 6 design alternates discussed, 3 that were agreed upon and 3 that were disagreed with. The first one really just being the control, leaving everything as it is. And then there was the fail-safe system, which we'll discuss what in the world that really means. But it would really ensure structural integrity and we believe would prevent any fatigue failure of the structure at all. The structural fatigue improvement is really just what does it look like to leave the overall design the same, but maybe change some little parameters, the thickness of various things, and see how that would increase the fatigue life. However, ground sleeves, welded stiffeners, and the improvement of the welds were not agreed upon during the industry advisor group meeting. So really the objectives that we're going to discuss in this presentation, some of the objectives of our project is to really show how we're creating a targeted testing program to isolate critical design parameters. As there's 1,000 different parameters, obviously you could change for cost structure, but we're really seeking to identify what are the most critical. We'll hopefully get to where we'll be providing recommendations for future connection design based on fatigue provisions. It was mentioned earlier that a lot of these cost structures, the design tables were maybe designed based on 1994 standards. And so there's a lot of fatigue provisions that may just not have been around at that point. And so we're hoping get fatigue into those designs, as well as discuss our progress in developing the database of cost. So getting into our fail-safe system, you can see it pictured on the right. How it would work is there'd be a threaded rod connected to the top of the structure, whether it be a TSS or COS, and it would be connected to the base plate of the structure, and you would tighten this threaded rod, essentially putting the pole and base plate into compression. And fatigue occurs when you have tension and cyclic loading, but if you put everything into compression, you eliminate all tension, and therefore you eliminate all potential fatigue damage. And so you should theoretically remove all fatigue failures. So here's what it would look like just on a structure-wide scale. You can see connecting the top of the pole being eccentrically loaded into the base plate. So for the structural fatigue improvement, again, just changing a few design parameters in the existing basis of the design. We've identified 8 main parameters that affect the fatigue life of structures on the left. And on the right, we have some equations from AASHTO that give stress concentration factors that can be used to calculate the hot spot stress within the pole to really figure out what is this localized stress causing these failures. So looking at the top equation is for round poles, and it's referenced in the bottom equation. For simplicity, we'll just focus on that top one. There's 4 real parameters here that AASHTO has said this is really what affects your fatigue life. You have the thickness of the pole, the diameter of the pole, you have your bolt circle ratio, which is the diameter of the circle of bolts over the diameter of the pole, and the thickness of the base plate. We don't feel like changing the diameter of the pole is the most economical decision to be done right now, so we're going to leave that as it is. And for constructability reasons, bringing the bolts closer to the pole doesn't seem super reasonable. And so the bolt circle ratio is also being left as it is, which leaves you with two important parameters, your thickness of the pole and your thickness of the base plate. And to demonstrate the importance of these factors, we'll look at the Dallas pole that failed as a case study. And so on the left, we have a bunch of different parameters of this pole. We really want to highlight the pole thickness and the base plate thickness. In the design tables, the thinnest pole you can have is 1/4 of an inch. So you can see this pole was just slightly thicker than that, a very thin pole. There was also a relatively thin base plate, with, I believe, the thinnest base plate in current standards being 1.5 inches. So we wanted to look at what would happen if you were to shift these numbers a little bit. So using the relative life equations in the previous presentation, we did some investigation. And we found that if you were to increase the base plate thickness only by 1/4 of an inch to a 2-inch base plate thickness, and increase the thickness of the pole by just one size to 0.31 inches, you would nearly double the estimated life of the pole. Where it failed after 11 years, we estimate that you might have gotten 20 years of life out of it. So it's a relatively simple solution, just changing some existing parameters that can have a pretty large effect. But as I mentioned before, we expect the fail-safe system might be a little bit more complex solution, but it should remove any fatigue issues that could potentially be experienced. So looking into our testing program, we've acquired 12 poles that have been in service, 11 TSS from Austin and Paris, and 1 cost structure from the Dallas district. Our testing setup is identical to the previous project, as you can see pictured on the bottom right. And a little bit more is that you can see here a little bit more detail on our test setup, how we're not just investigating what kind of stresses are we getting in the pole, but we're also focusing on how does the location of the pole, how does the location within the pole affect the stresses, whether it be at the bend or in the middle of one of the slats of the pole. And so currently we're just testing poles, getting an idea of their fatigue life with our test setup, but eventually we're going to put one of our fail-safe system poles into the test setup and put our theory into practice, and hopefully see that there's no fatigue issues there. So lastly, going into our cost database, there's many different variables that we are recording in our database. We've got this information through various different means. As you can see in the picture, we're there making some field inspections. There's some poles that we did field inspections on. There's some poles that we have TxDOT inspection records for. We got a lot of information from Google Earth and satellite imagery, and to kind of fill in the holes of what we weren't able to find from satellite imagery for pole thickness, for example, we use TxDOT design tables. So even more variables that we've recorded in the database, and really just want to highlight the wind map that we have been able to develop, as we feel like this will really help identify the risk involved with the various structures to better estimate the life. So if you're just pulling a bunch of information from Google Earth and satellite imagery, you probably want to verify it to make sure it's not a bunch of garbage. And so these are the 32 cost structures that we went out and identified. Here's just some methodology, some tools that we used. And then we also compared what did we see in the field versus what did we get in our database. And while there's maybe a little bit of error, we thought that we found that what we were able to get through Google Earth and satellite imagery was actually pretty reliable, especially for what we're hoping to do to really just identify risk with this database and just gather information. So we found there was a pretty good correlation, and we were very pleased with it. Here's just a little example of the massive information we might have for in our database. This is just 2 poles. So gathering lots of information that hopefully can be easily transferred into ArcGIS for later use. So here's where we have found all of our poles. We've located about 3,600 cost structures throughout Texas, Dallas and Fort Worth really being where the higher percentage of cost structures are. We have only identified cost structures with steel poles. For the sake of our database, we didn't pay attention to the ones with the concrete poles so much, but we really just wanted to focus on that metropolitan areas are really the areas of high risk. Not only in that, obviously they have a lot more poles, but potential failures just have a lot more consequences, whether it be risk to human life or economical dangers. So some conclusions that we have thus far in the state of our project is that it seems through all of our calculations and our design, the fail-safe system should drastically improve the structure's lifespan to being infinite as far as fatigue is concerned, as well as the geometry of structures can be altered even just by small amounts, 1/4 of an inch, 3/100 of an inch in some places, to pretty drastically improve fatigue life. As well as just in general, the high concentration of cost structures in highly populated areas makes it really crucial to understand and improve the fatigue life of these structures. Safety first, drive like Dixon. And there are correlations for friction angle now in our geotech manual. Figure 2.2 based mostly SPT results again, or SPT values. What is the status of the foundations for ancillary structures? Still, we're using our current standards are still using TCP, and they're not based on LRFD. And the TCP block counts are also used to get correlations for friction angle, shear strengths. Mostly doesn't change since we rely for those mostly based on the laboratory test results, either the UU test or the unconfined compression test. So what is research project 7236 about then? So basically the research is to develop standardized LRFD design methods for foundations of ancillary structures. The project number 7236 there. So that project started in last year, September. So it's about a year now. And they completed August 31st in 2026. Being done by TTI. Sorry, Texas State University, excuse me.
what are the objectives of the TAST? Primarily, it's developing LRFD design methods for foundations of ancillary structures. And this would be compliant again with the AASHTO LRFD requirements. And the other probably major thing is to update or replace the current standards that we have for foundations of ancillary structures. Again, this will also be in accordance with or compliant with the AASHTO LRFD requirements. So what is in the scope? This is again, since not being part of, the research team, getting plugged in kind of later, I may not be able to dig too deep into the research, but I'll try to present a high level or provide a very high level information. So as part of the research, the research team is looking at, or doing some literature review on what limit states are considered for the design for foundation design of ancillary structures. As you can see, these are some limit states that are considered by various DOTs across the country. And the other thing that they're also doing a literature review is on methods. What are the methods that some of these DOTs are using? As you can see here, mostly in sand and clay, the alpha method and the beta methods are used, which is also what's in AASHTO, and also our current geotech manual, the LRFD geotech manual for foundation design of bridges or other structures. For lateral load analysis, as we can see here, primarily most states are using PY curves. We are also using PY curves if you have done foundation designs for lateral loads. Mostly kind of the Oregon DOT, as you can see, would be using geotechnical fixity, or we keep increasing the depths until we get the deflection kind of to stabilize, right? The top of shaft deflection. But that's one of the things that the research team is looking at or doing in their literature reviews. So what else is in the scope? One of the other things that they're looking at is also existing correlations. You may be familiar with this correlation. We also have it in our in Appendix 2 of our current geotech manual. When we have SPT and TCP data, and occasionally when we wanted to convert one form to the other, we relied on this correlation. This is a result of a really old research project, but based off some of the data and analysis that they have done, they're getting some consistent results with this. The other thing is, what is the correlation between? They're evaluating correlations between SPT blow count with shear strengths and friction angle. TCP correlation with shear strengths and friction angle, and hopefully that would give us a very good sense of or good idea of how the parameters that we're getting are kind of tracking with our use of with design and use of the standards. Yeah. So as part of the correlations that they're looking at, this correlation here is in GC, or also in GC10. So based off CPT, bend shear pace, and SPT, there are some correlations. So they are also looking at this. See, the other tasks or the other aspect of the work includes comparing design's performance using the current standard with those, with that of LRFD approach or the new approach that we're going to be following for these type of structures. And comparing the performance of this with finite element analysis methods or models. And they will definitely be incorporating some of their findings with limit states, load factors for LRFD, and resistance factors, and also to anticipate some commentary on analysis methods for actual lateral moment in torsional capacities. This will take questions if you have any questions.
Good afternoon, everyone. It is a minute past 1. So the room is definitely less crowded than it was this morning, which is fine. David did pass around a packet of paper. It's traffic elevations. It's going to be part of the discussion for this presentation. If you didn't get one and you're interested in it, let me know. I think we have a couple more, but not a whole lot more. We can print more if you want it. I just want to thumbs up for those of you online. Can you hear us? All right, looks like we're good. Now trying to transition from eating to getting back into the groove of things. This presentation is going to be more give and take. It's going to be feedback. It's going to be more of a discussion. Sarah gets the fun one where you guys get actually be in our, raise cards up and all sorts of stuff. So mine's more technical, sorry. But I will be going over, it's called resources, it's documents, it's tools that we are in the process of developing. They are, I guess, more up-to-date versions of what we had discussed last year. Last year, you guys mentioned that you wanted to see it beforehand. I printed it out, I sent that out late yesterday, and so I also printed some out so you guys can have something to look at while we discuss this. So the first thing we're going to be talking about is working drawings. These are going to be those traffic elevations. And the intent of this is to give some clarification on when you use an SD sheet and when you don't. So a special zone sheet. So on your left, it's going to be, those tables that you fill out when you have something that's similar to a standard, but it's not fully a standard. So you can still use the tables, or you can mismatch different parts of the tables, like if you have a balanced T, things like that, where you're still using the standard designs and tables. You fill this out, you're like, okay, I know what you used engineering judgment or something, or you designed it yourself, but it's still within more or less standard, typical miscellaneous details, and you're signing it as a structural engineer. We find that this gets used sometimes. It doesn't get used all the time. Sometimes, even when we don't need it, we're not necessarily getting all the information that we need from a shop drawing review standpoint to review it. So we're having to make engineering judgment calls as a shop drawing review person as to what you mean when you reference a standard, right? It's the H cost Z1, right? Well, what is your design span that you're using? What is, if you have an extra deep sign, did you take that into consideration? Did you check sign area? Things like that. And our shop drawing review team, as you're doing a shop drawing, right? You're supposed to have contract plans, fabrication drawings, shop drawings, and the shop drawing should reflect the contract plans, or if the fabricator has alternate calculations, like for multi-sided and stuff, it should be matching that. And In some cases it does, in some cases it doesn't. And so we're trying to help clarify that and get all the information that we need on these elevation sheets. So that's why we kind of are leaning towards these working drawings, more or less a simplified elevation. Some of these can get really complicated, and I understand that, but we got to start somewhere. And we have tables. So again, there are some details that are on the SC sheets that we do need because they're details and assumptions that are on the design table sheets that if you're using an SC sheet, you're not using also the design table sheets. You might be using it for your engineering judgment and bringing it over to the SC sheet, but those details aren't there, are not part of the plan set for that structure. And so we are simplifying the special zone to have special kind of miscellaneous details, but we're getting rid of these tables and we're putting them on the elevation sheets. This is the intent behind this. We are open to comments, questions, criticisms, however you want to see it, but we are trying to move forward to get the information that we need for what we need. I know you can't read this. A lot of it is just, the pound sign saying, fill in a number. You know what the number is for your structure. The idea is that, this roadway is really going to be whatever your cross section is for your roadway at that point in time. But what we're trying to get across here is that, okay, we've got a cantilever, we've got different signs on it, there are different heights, they're in different locations. Our standards say, okay, we have a certain area that standard is good for. And if you say, and the way that our standards are written, it's a 10-foot deep sign. Now I know sign depths are getting bigger. And so as we do that, we're really looking more of an equivalent sign area. So one of the things that we did kind of on these tables that we're putting on there is we have the sign area. This is your sign area that you're putting on that structure at that point in time. And then we also want to put a maximum sign area as, if you have to replace that sign at some point, if you have to put it on a DMS sign instead of a conventional sign, like what is that equivalent maximum sign area that somebody can use that structure for in the future? It's also useful when we're looking at alternate calculations and things like that, that we can kind of we can compare to. So this is the minimum of what we need when we are looking at when you are using these standards, okay? So in a lot of cases, people just say, okay, it's the H cost Z1. It's the span length, which is from the edge of the sign to the center line of the pole. And by the way, there is trivia questions, hint, hint, wink, wink, in the next presentation, according to the span length. Anyways, but okay, so you've got your design span length that you're going into that table for. You've got your design tower height, and then you've got your design wind height. So if someone's using an H cost, I'm going to assume that this design wind height is greater than 33 feet, which is why you have to kind of bump it up. But all of this information is important. You choose which standard you do, and then you've got your span length and your tower height. You go into it. So this is really just telling you, okay, this is my design span. This is the area of the sign that I have. This is the area of the sign that's on that standard, if it is directly applicable to that standard. This is the height. So from this, we can go into our design tables and find that information. So at that point, we'd find out the outside diameter of the tower and the wall thickness. These are important when we're looking at alternate calculations. So somebody comes back and they're doing a multi-sided. This is something that is good to know kind of off the top of the head, and okay, what is the structure? We have shear, torsion, and moment here, and this is really to help with kind of the foundational design, knowing, and when you come back later and you're looking at this, okay, I used the standard, but what was that actually to? having these reactions here means that when you go back to that elevation view, you know exactly what that pole and that connection was designed to. It doesn't necessarily matter which standard, which version of the standard, you know what the reactions are that you designed for. So we're trying to think, what do we need now? What do we need for shop drawings? And what do we need on the sheet for future reference that would make things easier? And then you pick out your drilled shaft diameter, you determine your soil, and then our current standards are to the TCP, not to the SPT, right? So that's one of those things that we are moving forward with. But right now, these tables are intended to be used for what we have currently. One of the things that we're adding to these sheets, especially for the cost structures, is, okay, what do we do if I have a DMS sign? So in our general notes, we do say that you multiply the essentially effective sign area by 1.42, and this is to account for the extra or the larger drag coefficient on the DMS sign. Since we are using the LTS 3 and 6 kind of for our designs at the moment, we're still using the 1.7 drag coefficient for DMS signs. I know in more recent LRFD ones, they've done research and they've taken that away, but we have not implemented that yet. So to find a maximum sign area, right? It's the design span times 10 feet. That is what our standard says. That is what we have. So when you look over here, and if you're in zone 4 and you're using a COSI for your factor for kind of wind zone is 1.0, your sign area is going to be this equivalent, is going to be the 10 feet times your design span. I am getting somewhere with this, I promise. I'm not trying to do just equations, but I'm trying to kind of give you guys an idea of where we're coming from with this. The other thing is sometimes we've seen things that are over 50 feet. So for our wind design height over 50 feet, our standards are not directly applicable either. So what we're trying to give you here is factors so that, say, if you are at 60 feet, right, you can reduce the sign area, and that essentially reduces it for the increase in your wind load due to the height of the wind. Also, okay, I'm in zone 4. That's actually really good because I can actually, if I use a COSI 3 with that design span and that design height, I actually get 31% increase in the sign area that I'm allowed for that because it's being designed for a higher wind speed. I mean, you can get up to 2 times if you're in COSI 4, but so depending on whatever your wind zone is, you can determine which one of these standards you want to use, and you can adjust your maximum sign area accordingly. So based off of your wind zone, increased load of the wind, or if you need to play around with your height because you're over that 50-foot design wind height. So we have this lovely equation that just says multiply all the factors together. And that will give you your maximum sign area, depending on what standard you have chosen and what your design height is. Okay. We are trying to simplify this. We are trying to give you guys this guidance. This is what we've come up with as how we feel it would be the most helpful. Is that you've got this working drawing for a cantilever structure, and you have these factors that you can use, and you can determine your max sign area, and you can determine what standard you're wanting to use for that. So if you come back here, when you talk about, okay, which standard are you pulling this information from, right? You're determining it based off of what factor you need to get your maximum sign area above your actual sign area. Okay. So I went into a lot of detail on this one. This is the only working drawing that has this much detail on it. We're still working on kind of developing the other ones to have this guidance on there. We do have the working drawings for a balanced cantilever as well. This is going to be mainly, we see this a lot with DMS signs. We do have a larger table for that one. The examples that we have right now and the guidance that we've kind of been using right now is for your truss members, you're going to be using your cantilever. So really it's half your span length for a balanced T. But when you do your tower pipe and your base plate connection and all that information, you're doing it for the actual span length, right? So typically this is 30 feet, and that's what you're basing your pole, your drilled shaft, your base plate connections on. And then your truss is based off your 15-foot cantilever. That being said, it's not, I go into this table and I have this span, design span length, and I have this height, and I go across and go, okay, these are my values. No, it's for my truss, I'm going to this span and this height, and these are my values. And then for the information for the tower, I'm going to this span and this height. There are ways to simplify the table where we do specify truss, like applicable standard design span, design height for truss details, and then you also then define that for your drilled shafts and your tower pipe, right? So we could simplify it, but when we're just saying, okay, refer to these standards, the person that's doing the shop drawing review is like, okay, and even like if they have an SD sheet, right? They're looking at it going, okay, where did they get these values? Did they do this half a cantilever, half the span, and then the full span for the tower? How did they get it? And that kind of leaves them where they're kind of doing engineering judgment calls, and that's not where we want our shop drawing review team, right? I know me as an engineer of record, if I made certain assumptions and I signed off on it, I wouldn't want somebody else going, well, maybe this was their intent. If my details aren't clear, I would want somebody to come back to me and say my details aren't clear. And so recently we have been going back to the EORs a lot more, going back to the districts going, okay, this is what we're seeing. This is what we're assuming your intent is. Confirm that the engineer of record used their engineering judgment and said that this is what they actually wanted so that we can proceed with shop drawing review. Sometimes this comes back in a change order or not, but the idea is that we want to go back to the engineer of record to confirm their intent if it's not clear on the sheets. All right, so we also have them for OSBs, so the overhead sign bridges. Again, different sign areas, depths, same kind of concept. It is a design span, design height. You go into a table, you pull it. So it's the simplified table, right? And then for the OSB, where it's the cantilever on the end. So we do currently have examples that kind of walk you through how you're supposed to do this, how you calculate where that splice actually is. And as time goes on, the people that created these designs, these examples and understood the basis for them and how to use them, they're not necessarily around. We've got other people coming in and they aren't necessarily getting interpreted the way the intent was at the beginning. And so we're trying to clarify this by then having the engineer, if they are using different spans throughout the tables and pulling information, that they are putting all the information on the working drawing elevation. And this is, so again, the shop drawing review person and the fabricator, this is going to help the fabricator too, right? There's a lot of times where the fabricator, we get shop drawings and we're like, oh, where did that come from? Because we're looking at the contract plans and it's not there. And so they're doing their best guess based off their experience and stuff to try to fill in the holes because the project is on schedule, right? And they're trying to get things out for the contractor. So this is just making it clear what the intent is from the EOR. And I'm going to stop there. That was a lot of information. Are there any thoughts or questions regarding the elevation working drawings? Do you guys think they're going to be helpful? Are they more of a hindrance? Are there, thoughts and ways that they can be improved? And I open the floor up to comments. Yeah, Sarah, we should have started with yours. All right, do we need to do some stretch reflex and like get the blood pumping again? Are there any questions or comments online? There. Okay. Yes, Stephen.
Asking.
Yes, so typically it is the roadway designer who is, or even, the traffic designer, right? Depending on what hat they're wearing that day, that creates these elevation sheets. What I have seen when Tim was here is like whenever we did one, we signed to them. And so you'll see on these working elevation drawings, there is, here's the roadway or traffic person signature, and here's the structural engineer to make it, because sometimes it's not clear that, hey, these really are structural designs. So if all you're doing is pulling from a table, go for it. But if you are trying to use engineering judgment and pull from multiple tables, and you might not know exactly how the information came about and how to apply it, right? Then those really should be more on the structural engineer side to do that. And with this is one of the reasons why we have started the pre-certification for the overhead sign structures and things like that. So is to make it more awareness out there that they really are structural details, especially when they're spanning over a roadway. One thing I guess I wasn't extremely clear on. So bridge division is responsible for the structural aspects of traffic structures when there's a risk to the public, okay? So if it's spanning over a roadway, high mast illumination poles don't span over a roadway, but if they fall down, they're probably gonna go over a roadway. So when there's a higher risk, traffic signal poles, things like that. The large guide signs, the pedestrian poles where you push the button, those don't pose a high risk to the public, and those are traffics, right? We don't need, if they have an issue, they do come and they do consult us and we do work with them on it. But in general, that's outside of the realm within bridge division when we're looking at structural aspects. And making awareness that, hey, these structures are going over the roadways. They do pose a risk, right? We need to make that awareness, and that they need to be looked at as structural details. That kind of cover what you and we've been trying. We have had more webinars. I mean, starting the TASIG group. There are district TxDOT district people as well as design consultants that come to this, and so we are trying. Yes. So these sheets currently, how we have it, is more of when you're using the general standard angle sizes, panel sizes, things like that, but the standards aren't directly applicable, right? The standards are for conventional signs, 10-foot deep, design span, length. So if you've got 20-foot tall and it's on the very edge of your cantilever, you might be in the sign area realm, but you're going to have more moment because it's all out the end, right? And so we need some awareness of that. So when it's not directly applicable to the standards, but they're using those details, then the SD sheet should be filled in. Let's see. And it's not necessarily getting filled in. It's been more of a using notes to point the fabricators and the shop drawing people to the tables for them then to interpret what's being used for the truss and what's being used for the column. Another thing is sometimes these are put in here, but they're not signed and sealed. Sometimes they're put in here and the general notes are referring to the standards. So the standards are also put in there. I mean, if you, so say you have one sign structure, which is probably not gonna happen, but you put in an SD sheet and then you put in the design tables and your elevation view is pointing to the standard sheets, right? Based on precedence of our construction specification, the sign sheet overrides the standards. But if you got people that might not know exactly, those standard sets and things like that, it's very confusing, right? Because you've got a sheet that's referring to standards that shouldn't even be in there, right? And so we're trying to help clarify that, trying to help people be aware of the information that is needed for the fabricator and for the shop plan review, right? So we're trying to get away from this. In all sheets, we have this elevation view when we have a sign structure, right? It's just, it doesn't necessarily have this table. And so most of the time when this is being done, it's pretty straightforward. You've got a roadway engineer, a traffic engineer that's creating this and then put, copies and pastes from a previous project, what they think is enough information. So the idea is that if we say, here's the table, this is what we need, then we can get that. Because I know, like, if I was given a project and say, hey, just do this, and I don't have any go by, where do I start? Am I going to have everything there or not? Yes.
I think it was even sentiments that traffic, my experience, traffic is always what they have problems.
Right. And so again, that's why, so these working drawings will be posted on the traffic's website in the area of the overhead sign structures. So they will be there and they will be like, oh, here's a working drawing for an elevation. What do I need on it, right? We're trying to get the information out there. We're trying to make it then available. We haven't done that yet. We wanted feedback. We're still trying to help with like the design considerations, right? Like if I have a DMS sign, oh, I, do 1.2 or 1.42 times the sign area. That's what the sign area actually have because of the drag coefficient. Which standard do I use that covers that for the maximum sign area? So I would say a roadway engineer or a traffic engineer could follow that guidance and do it without necessarily having a structural engineer. But so that's what we're trying to put out there. Yes. So the materials that should be used on it should be in the standard details, right? 99% of the information is there. And part of the update that we're doing for the cost in the OSB, right, is also going to help with that. And there's no longer going to be these brackets for number of bolts. We actually have a column that says number of bolts so that you know what that number means. Things like that. So we've been trying to clarify some of those things as we move forward as well. I would say from a fabricator's standpoint, is it better to have the material on the elevation? I would think that you'd want it with the details that you're trying to fabricate. So like the materials would be more on the miscellaneous details and things like that. But I'm not a fabricator, you are, so what would help with that?
Your A50 grade B or A501 grade.
Mhm.
But for us, we try to do this very material, the industry can provide, they did, and although it does say, over. But, your, expectation was a big standard of design. So that's really what I want. When can we use it? It is as.
Right, and so part of the packet that I had sent out, I didn't print it out because it's 26 pages, but it is the design tables for the update for the LRFD. And my request specifically for that packet is for the fabricators to look through it and comment, like, what is available? And I have already gotten one email back for feedback. It included material as well as sizes, and so please send that our way so that when we're wanting to take the time before we post it to incorporate the material changes and the material availability into it. So,
Same thing happens for our base.
right, so what I asked from you and all the fabricators is that you let me know what is readily available. Like, A, what is available, and B, what is readily available, because we're gonna most likely wanna go with readily available, but sometimes maybe we need the one that's available, but it's harder to procure. But we need that information.
Sometimes in a situation of like, we could spend more money on a 178. than we can do it.
Right.
Yeah, ridiculous as it is, it's because of 178.
Yeah.
It's like 5/16, they're gonna see that, right? 2 by 5/16.
That gets used to.
3/8, what do you think? Kind of weight difference. That's why our design, we typically would size up, not use 5/16. but 3/8. So.
Right.
That's it.
Right.
Hey, he didn't want.
Right, and that's kind of the information that we're wanting, which is why I sent out the material, the design tables, is so that we can get that information. And so I am also over the shop plan review team within Bridge Division. So the discussion does come up a lot, like, some of it's labeling, some of it's thickness, and it's for different things. And so we have some tolerances that we're, okay, we can accept that, and we have some that are like, okay, we need to go to the UR to verify, because it could change something within their design. Like a 1/16 of an inch thickness, we usually, we'll go with it, as long as it's bigger. Right? So, but again, the reviewers have to take it up to an engineer to make an engineering call, one way or the other. And so, but we do have some things like that. But I would just like to know what is available so that we don't have all these sizes that nobody wants to spend their money on or get.
When I get back home.
Yeah. I'd appreciate that. So. Okay, anything else on the working drawings? If there's certain email distribution or a certain way for me to get the information for these elevation working drawings to traffic and roadway at the district level, I am open to suggestions. So, I mean, the TASIG does have traffic and, maintenance and MTD, and we're all working together on this, right? But I think it's more at like the district level that we need help. So if you can help me spread the word, that'd be great. Anything else? Anything online, Sarah? Okay. Now, we are trying to help you with this. So we're not just saying, hey, there's this huge table, fill it out. We are creating spreadsheet tools. So, last year, the one that we had was working together with like which standards do you need to pull and things like that. As we were working through it, we were trying to put too much into one spreadsheet. And so we've kind of go the route of, okay, here's one for costs and here's one for OSB. And we're starting back with like the information or the table, right? So this spreadsheet, you enter this information, it'll tell you what your maximum area is. It will give you suggestions as to whether or not you should be using that standard, or if that standard is not good. Down here it says bad. I like it. It turns red and it says bad. But it gives you the information that you need, right, to make the decisions. And then it has a table that you can then import into your working drawing. So we are trying to give you guys the tools to make it as easy as we can. Along with this, we will be incorporating kind of like which standards do you need back into it. But we had to kind of take a step back and say, okay, costs, OSB, because especially with the design parameters and stuff, they're two different types of structures. So we are working on that. This is another one of those top priorities for me, is getting these working drawings out, as well as these spreadsheets, so that we start getting the information that we need. The other one is getting the cost and OSB standards updated from the fatigue standpoint and things like that. And we are getting close to all of it. So I did send the spreadsheet with the files yesterday. One thing to note, this is not the production. So it's not ready to post yet. We are confident kind of in the numbers and things like that, but there are some other things that we want to add to it, a little bit more troubleshooting with it before we post it, because we do want to do all the reviews so that we're not putting something out there that we get a lot of emails back going, this is coming back with no good or not spitting out values, or so we're trying to troubleshoot it with how many ways can we input this information and does it give answers, right? So I mean, you guys can play around with it and tell us if there's different situations and things like that, other information that you would want on it. We do welcome the feedback. Yes.
Quick question on the TxDOT. How the LRP is moving on paper.
Mm-hmm.
I'm guessing it's
So there was a presentation last year. It's a very good presentation. It is on the website. And Ryan Eves went through how do you use the current TCP charts with the new LRFD, SPT, and stuff like that. We are moving away from it. So when we do update the OSB and the cost, right? I believe that it does go to the LRFD foundations. Been a while since we've had that discussion, but I do believe we went that way. But we also, I mean, we have people using the standards now. We want to give tools to what we're doing now while we're also working towards the future. Bob?
I have a question. I was wondering if that table that it kind of like filled out on the editor and stuff like that table is working on it. Maybe you did transfer the information to the people.
Yes. There's a couple of them that aren't quite lining up perfectly, but when we do post it, it will be exact. Yeah. And so in Bridge Division, we do use Axiom. And so having the Excel table, we can just Axiom in the table. Anything on this? I just wanted to let you guys know that we are trying to do a table, because especially when you see the very long tables, you're like, oh, I have to put in how many values? And so we're trying to give you tools just to import the information. Anything online, Sarah? All right. So then what else are we doing? Yeah, so I didn't quite get there. This is the working drawing. Here's the table. Here's the information in it. Okay. Ancillary structure guidance. So the 1990 bridge design manual had ancillary structures in it. The 2026 revision that we are currently working on will have ancillary structures back in it. It will give you guidance on if you have a one-off structure that's completely not anything our standards cover, which specifications are approved to be used, and some other, what I would say is useful information. And I'll get into that in a minute. But so I just wanted to let you guys know we are also, so we have the working drawings that kind of give you an idea of how to use the standards with factors, and then we're going to have, you know, official guidance, material properties, things like that in the bridge division or the bridge design manual update that we're working on. That will also have the 10th edition ASH book. So it's a big update. Okay, LRFD costs and OSB updates. So this is just kind of a couple snippets from that huge packet I sent. So, you know, looking at tower pipes, you know, what diameter pipe, what thickness, what material, what can we get? Our truss angles. I'm pretty sure there's probably a 5/16 in here. No, it does say 3/16, but you know, the number of bolts. I know there's been discussions on base plate material recently. There's been discussions on, I think, anchor bolt material and stuff like that too. There's been a lot of material discussions recently. So we want to get some of that stuff, but these design tables is going to be what helps us. We also have them for the OSBs. Again, angles. This is going to be the tower legs. Now, this is something I want to bring up. This is guidance that will be in the bridge design manual when we update it. There is averaging of the type or of the tower heights, right? So the tower legs, you have a right and a left. Within reason, you can average them, use the W shape for the average, not a problem. One came through last week where we had a 6-foot leg and a 45-foot leg, and it was averaged, and they used the average. And so this is, again, where I come back to engineering judgment. When you start getting a 45-foot column is really tall, you start talking about unbraced length, right? It's not a compression or a tension strength. It's an, you know, unbraced length. You've got two tower legs, one's in compression, one's in tension. A lot of the discussion that we have is about the uplift and the tension and checking the bolts and stuff for that. But when you start getting really tall columns, the compression is a concern. I'm pretty sure most people in here understand that, but not everybody does. So we do have, this is kind of a note that we put on kind of as a caveat to the new standards. We're talking about like, okay, these designs were for a 10-foot differential. So if you have a 20-foot and a 30-foot, average them, right? Use 25-foot. The one I was looking at, it was a W14 was the average, and a W21 is what the 45-foot one, right? So if you're talking about W10 versus 12, 14 versus 16, right, you're within reason. But when you need significantly different, we do need engineering judgment plays a part. So, and we do have a disclaimer in all of our standards that says you use them at your own discretion with your own engineering judgment and make sure it's applicable to your project. This is the same slide from last year. You know, I have to put 3D modeling in my presentation somewhere. This past year, we actually were looking at 3D cells for roadway illumination poles and making those dynamic. It was funny. So Bentley was showing us how we can easily do it. It looks simple. It's not as simple for our roadway illumination poles. Let me just say that. It's like the angle that the pole comes out along with the taper and everything. They're like, oh yeah, it's TxDOT. So, I mean, it's not that it can't be done, and we do have it, but we are looking at trying to get 3D cells also for like digital delivery and things like that. That is my presentation.
Are we back online? Could you throw some thumbs up, virtual audience, if you can hear us again? Okay. Pretend that didn't happen. All righty. Do you all give up on this one yet, or did you all figure it out? Oh my goodness. Y'all come work in shop plan review. You're welcome. So there are the differences if you didn't spot all of them. Why does that matter? Why did I even bring that up? That's just another example of little changes can be hard to notice if you're not aware, right? So let's use big clouds and notes and circles and callouts and be very explicit if there's a change, because if I'm reviewing something and halfway through we go, oh, something changed, here's an update. Do I want to start from scratch? Probably not. So let's highlight those deviations. Why are we having deviations? Because things don't always go right. So I'm not going to go through these because it's the end of the day, but I did throw this in here for your reference because you guys will have access to these slides. But what should I do when something goes wrong? There's a couple different scenarios depending on who finds the error. The main thing that I want you to remember, those 4 parties involved, they all need to know about the error, because if just 2 of them know and plans get changed and the 2 others don't know about that change, we got a problem. So keep that in mind. If there's a change order or any sort of adjustment, everyone needs to be on the same page and what the plan is going forward. So you can study those when the problem pops up, follow that flow chart. Okay, I don't have color codes for this one, but I did want you to study it a little bit. Can you spot an error on here? I'm so sorry. So slow. Good old TxDOT Wi-Fi. Let me repeat. Please study the truss, and can you spot anything wrong with it? Does someone want to be brave and raise their hand and offer up what they think? Yes, sir. Me? All right, we got a couple in agreement there. There you go. So I'm giving it. It's very slow now because of but the main thing that we want to talk about is if you're not really paying attention, that might look right. If I'm driving under the fallen sign structure, you know, what's the difference there? But these are the things that are getting reviewed in the shop plans. These are the mistakes that we're trying to catch before any sort of construction is happening. So little details matter, and that's what we want to be focused on. I will give it 10 minutes to upload to our next one. Maybe. That's real slow. That's all right. We got the main point across. There we go. It was probably the animations that threw it off there. So shout out to the shop plan review team, put these slides together for me, and they're very nice. When they said, oh, you accidentally grabbed the salt instead of the sugar, I probably would have written this as, you ever swapped out the salt and sugar to play a prank on someone? But that's the difference there. But we've all been in that situation. You want to add a little sweetness to your coffee, and you have to take a risk when there are 2 of these identical containers on your table. what is the point I'm trying to get across there is that it matters. Labels matter. So we have big packages. It might seem like overkill to have all the project information on every sheet, but this is how we stay organized. And we talked about double checking details. It's all part of that organization and keeping everything how you want it together. Those are the trivia I have for you guys today. In short, make sure you have good shop plans so they don't get rejected. It has to be buildable, right? Or else it won't. So thank you for putting up with me. We'll probably have a little discussion on shop plan questions, but if you keep your cards and paperclip on the table, we'll clean it up after you all go. So thank you.
So as you can see, she's the better half of the bridge design section. A lot more entertaining over there. So that is all as far as the presentations that we have today. Are there any outstanding questions or thoughts that anybody wants to share before we kind of wrap things up? Okay, let's see. Anything online? Refresh my QA. It looks like it's all audio issues. Imagine that. You know, when your Wi-Fi goes out, your audio tends to go out too. Okay, so I really do want to thank everybody for showing up. It's a privilege to be part of this and help get everybody together. This is a big effort, as you can see. When things went down, there were like 5 different people like swarmed around. This wouldn't be possible without every single person that's helping with it. And I really do value us having the open communication and working together, and send any feedback or anything else. We will be looking for topics for next time. We do virtual ones when there's a specific reason to halfway through. We've only had 1 or 2 of those. Other than that, it's the annual hybrid, and I do really appreciate everyone coming in person and being here. So with that, I'll let you guys go. Thank you.